Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure today to welcome Ryan Newton from MIT. Ryan is finishing his PhD there and is going to talk to us about some work that is of great interest to me because it combines both programming languages and systems research. So, Ryan.
Thank you very much, Jim. Oh, we do have the speakers on here. So hello and good morning. Thanks for making it out and thanks for inviting me to speak today. I'm going to be talking to you about the WaveScope project, which was part of my thesis work at MIT. And this is a talk about a parallel and distributed programming model. But it's very applications-driven research. So I'm going to go ahead and start by telling you a little bit about the applications that we've worked on. So this is a system for locating animals based on the sounds that they make. And we've used it for a variety of bird species. But the critter in the upper left there is a marmot, a large rodent native to the southwest of the United States. I don't know if you get them up here in the northwest. Anybody seen marmots in Seattle? OK, around Seattle. Excellent. Well, marmots, unlike most rodents that you may be familiar with, make very loud sounds when they're scared. So this is a marmot alarm call, something like that. And they make one of these alarm calls whenever they're frightened by a predator, or in our case, for testing purposes, by a graduate student charging at them. And based on those sounds that they make, we can locate them using a microphone array. So the platform that we used in this deployment was our prototype VoxNet platform. This is an embedded Linux-based platform with an ARM microcontroller where each node has a fixed array of 4 microphones on top of it. And there's a low-power Mica 2 moat that can duty cycle the more powerful components in the system. And we deployed 8 of these nodes throughout a meadow riddled with marmot burrows in Gothic, Colorado in August 2007. So this was the deployment that I did with a lab mate from MIT, as well as with some people from UCLA biology. So this is a relatively high data rate embedded sensing application. And this gives you a little bit of a sense for the kinds of things that we're working on. We've also used WaveScope in the context of several other applications in our lab in collaboration with different groups. So in addition to locating marmots, we've worked on pothole detection using a fleet of taxis that are equipped with our sensor packages that have accelerometer and GPS. And we use this to build a map of the worst potholes in the Boston area. Although if any of you have been to Boston, the more well-posed problem might be detecting non-potholes. And we've also worked on some computer vision applications, this one in California, using camera sensor networks, as well as pipeline leak detection in water pipelines using vibrational sensors. We've done some speaker detection and speaker identification using any embedded device that has a microphone, such as a cell phone. And finally, we've done some EEG seizure onset detection using 22 channels of EEG data that come from leads on the head and go to an embedded device. Now, today, I'm going to use all 3 of these applications in the context of doing an evaluation. So just bear those in mind a little bit. And the relevant features of these applications that I want you to take away here are that each of them has a processing structure that can be expressed as a collection of independent tasks communicating via data streams. So I'm going to go ahead and call that a dataflow graph, and we'll be talking about dataflow graphs a lot. And somewhat uniquely to these embedded sensing domains, we see a combination of very regular processing, often near the sensor inputs where audio or video data is streaming in, with very irregular processing because you detect a marmot, event-triggered computation. And one of the key challenges in doing this range of applications is dealing with all of the heterogeneous hardware and software platforms that are involved. And that heterogeneity starts with the software environments. So in one of these embedded sensing applications, we'll typically have at least 3 different platforms involved. We'll have very low-power sensors. We'll have a base station, typically a laptop or a desktop, something that's on the server side or back end where the data is feeding to over here. And then we'll typically have something in the middle, often a microserver, such as the VoxNet platform I showed you, or a smartphone with capabilities somewhere in the middle. Now, these are programmed using totally disjoint software environments, of course. We have all our usual languages and tools that we use on our desktop. And we have a different set of SDKs and environments and tools that we use for programming our smartphones nowadays. And then we have yet another set of operating systems, languages, and tools that we use on our low-power embedded devices. And so this is a big mess. If I want to write a piece of software that targets all of these components, I have a lot of work ahead of me, partially because of the software heterogeneity. And programming models for sensor networks has been an active area of research for the last several years because it's recognized to be a difficult problem. And a lot of the work in this area has focused on capturing communication idioms in large networks of these low-powered devices, including some of my own previous work on the regiment system. But none of these systems were broadly portable across different classes of devices until the WaveScope system that I'm talking about today. And the goals of the WaveScope system are threefold. So as with many of these other efforts, we want to bring higher level features to very small platforms. We want to make it easier to program these devices. But we also want to pay close attention to the life cycle in doing one of the kinds of applications that we're working on. So first, you have to somehow prototype your application, perhaps in MATLAB, prototype the algorithm, assess the hardware requirements, pick a platform, buy it, and implement your system. And then later on down the road, if the hardware gets upgraded, you might be able to change the application. If the application requirements change, you might need to change the hardware. So addressing these lifecycle issues requires a somewhat different focus on the tools. And one of the implications of this is that it needs to be very easy to move computation around between different parts of this picture. And that's a requirement of our system, that computation is easily migratable between these heterogeneous platforms. So given that motivation, the rest of the talk is going to look like this. First, I'm going to be talking to you about the high-level WaveScope design. And then in the second part of the talk, I'm going to put on my compiler's hat, and we're going to talk about optimizing software that's written for this kind of environment. And in the third part, we're going to talk about the deeper problem of automatically partitioning applications across different kinds of devices. OK, so a bit of background. Parallel models of computation have been around for a long time, obviously. And in particular, languages and compilers that have extensions for streaming or for parallel processing are also quite old. So a lot of these earlier systems were quite elegant in general, but also had some disadvantages, which is why we're still working on this problem today. So a lot of these systems were unsuitable for static analysis and made it very difficult to leverage domain-specific optimizations, such as in the domain of digital signal processing. And this made it hard to extract scalable parallel performance. So recently, there's been a lot of focus on stream programming in the last few years. And a lot of this renewed interest has come from a systems and architecture community, specifically with a focus on parallel performance. So we see systems like these, for example, frequently motivated by particular parallel architectures that people want to program. The StreamIt system is a synchronous dataflow-based streaming language that came along with tiled architectures like RAW. And the Brook language was around for programming GPUs. But at the same time, a different community was focusing on the problem of streaming, and that was the database community. And they came up with systems like Aurora and Stanford Stream. And they were interested in a different set of applications, financial applications, for example, where data rates are irregular, and stock ticks and what have you. And so they picked up an asynchronous dataflow model instead. And likewise, the literature in this area is focused largely on dynamic optimization and dynamic scheduling, rather than static scheduling and optimization that is appropriate to a synchronous dataflow model, such as you see in digital signal processing or graphics applications, where the data rates on all the edges in one of these dataflow graphs are known. Now, there are advantages to both of these sets of systems. So on the top here, these synchronous dataflow systems can be extremely fast, and they can exhibit great parallel speedups on a variety of different architectures. Whereas these asynchronous dataflow-based systems we see in the database stream processing world offer a great degree of flexibility in the kinds of applications that they can handle. So we actually tried starting off prototyping some of the sensing applications that we worked on using these different systems, in particular Aurora and StreamIt. But for various reasons, we ran into problems, and we ended up needing to build our own. And there, WaveScope was born. And part of the goal of WaveScope was to combine some of the desirable attributes of these different approaches. And in particular, WaveScope takes a very profile-driven, empirical approach to scheduling and dividing dataflow graphs. We're going to pump sample data through a dataflow graph and observe when the data rates are regular, and then we can leverage techniques from this community. Otherwise, fall back to more dynamic techniques. All right, so just to give you a little, I'm not going to belabor the syntax here, but just to give you a little bit of a sense of what it's like to program with WaveScope, there's one important keyword that I need to tell you about, and that's iterate. So iterate is a for each statement over a stream. So a stream is an ordered sequence of values that are going to appear at some time, and we want to assign a name to every value in the stream. And when this introduces a single dataflow operator in our dataflow graph that we're constructing, with one input and one output. When an element becomes available on the input stream, we execute a block of code that goes inside those curly braces. So this is a very simple example here. Emit is going to send output on the output channel. So all this does is take a number on the input, and if it's even, emit 2 copies of it. Otherwise, emit 1 copy of it. So for example, if we get a 4, we'll fire and emit 2 4s on the output. And the return value of one of these iterate statements is just a stream itself. So we can assign a name to it, defining the stream S2 in terms of the stream S. And we can use it anywhere in the program that we like. We can define functions that take streams as input and return streams as output that they build with iterate. And we could run a loop like this that will invoke foo several times to accumulate a chain of dataflow operators that would look something like that. OK, so switching from the source model to the execution model. Once we have one of these dataflow graphs, how does it execute at runtime? Well, there are lots of different choices in terms of picking a dataflow model. I mentioned that we're going to have an asynchronous dataflow model, in particular a non-deterministic asynchronous dataflow model. And let me show you what that means. So here's our dataflow operator introduced via an iterate. That was our example iterate from the previous slide. The dataflow operator has some code inside it, visualized by those lines. And when an element becomes available, we have to fire atomically, execute for some length of time, and produce 0 or more outputs on our output channel. And so you could think of this as an event or an interrupt. There's no back pressure here. It must be handled when the event occurs and when the scheduler decides to invoke the dataflow operator. So the output here, S2, is a value that can be consumed in multiple places, and that gives us fan out in the model. First, let me tell you about statefulness. So these dataflow operators can be stateful. They optionally can have private state that they maintain between invocations. But the rule here for this particular model is that there's no shared state. So it's not allowed for another dataflow operator to touch that same state. That's prohibited by the model.
Good question. Does iterate operate on every individual input data, whatever you call it?
Yes, that's right.
Token or event. Can you specify like I'll fire after like 100 of them?
So that would be so that's an example of a simple optimization. If you were taking very fine-grained inputs, you would want the implementation to only invoke every 100.
So every single event will trigger firing.
Yes, that's the model.
If you ignore it and don't do anything, but you will get fired.
Yes, that's right. That's right. So you don't have any particular control over the channel that's coming in. The API is simply when you it's a for each type model. It's a loop, and for every element you're running one iteration of the loop. OK, so as I started to say, we get fan out by consuming S2 in multiple places at multiple downstream operators. That's fine. Now, to tell you, I need to tell you about one more primitive operator in the system that gives us fan in, and that's merge. So merge takes 2 streams as input and interleaves them in the real-time order that they arrive. And so that makes it a non-deterministic merge, and that's what makes our dataflow model a non-deterministic dataflow model. So these 2 primitive operators are what everything in the system is built in terms of. And I'll tell you about more complex synchronization policies, for example, between 2 different streams, and those are built up using merges and iterates. That's the real core abstraction. So this system I'm talking about deals in terms of dataflow graphs. An application is a complete dataflow graph with a fixed set of connections. And we can think of each one of these operators as containing some code in a portable intermediate language that can retarget to all the different devices we're interested in programming. So the system architecture here consists of back-end code generators that can target each of these different classes of devices that we're interested in. So ultimately, the application needs to be split up into disjoint subgraphs that are then assigned to particular devices. And a back-end code generator will. John?
Yes. For all these, so you say it's a fixed set of operators, or fixed set of operators?
Right.
So is that just something the compiler enforces, where if you've written code that has some kind of conditional around whether, and then hidden within that is whether an operator gets created, then it barfs there and says you can't do that?
Yes, well, you just can't construct something like that. There's no API provided for adding or removing operators at runtime. The kind of extreme, if we put up synchronous dataflow on one end, the other extreme would be some of these models, in particular that they use for the streaming databases, allow you to dynamically change the dataflow graph. Or something like Erlang, where the set of actors and the messaging relationships are totally dynamic. So in this, we still have a lot of information about what the actors are and who's communicating to who, but we don't know necessarily what the data rates are. So we've taken 2 small steps away from synchronous dataflow.
Any reason you choose non-deterministic dataflow versus there are plenty of deterministic models?
Sure. So certainly determinism is a nice property when you can keep it, and that's one of the primary advantages of synchronous data flow. But in this case, the merge I showed you, it merges things in real time. So frequently you want to do a sort of select statement over two real-time sources of events. You don't statically have any knowledge over which one's going to happen first. You might want to call this indeterministic instead of non-deterministic, if you're familiar with that distinction.
Can you use timestamp or other things to...
Yes, you could make a deterministic model in terms of timestamps.
But you should not.
Yeah, it doesn't. We found that it doesn't help us. And it's not assumed that that we have timestamps in a single global clock for all of the different tokens in the system, because of course we are operating in distributed environments, and time sync is another issue. But I'd be happy to get into a little more detail on that offline. OK, so I wanted to give you a little bit of an idea of what's involved in trying to target one of these small platforms. So the smallest platforms that we target are these TinyOS nodes. And these are small indeed, with 8 or 16-bit microcontrollers, with 2 to 10K of RAM, and with no memory protection in the operating system. TinyOS is a common one, and no thread support. So none of the features that make programming easier that we're all familiar with. And there's, of course, been a lot of research in trying to get some of these features back into these small platforms, like the work on proto-threads, and also like what I'm going to show you on this slide. So in this slide, I'm going to address how we target our abstract data flow model to this very small platform, addressing both data granularity and computation granularity. So first, in the WaveScope model, one of these data flow operators can, when it fires, it can take a data structure in and execute for an arbitrary length of time and produce some arbitrarily complex data flow or data structures on the output side. So in particular, on the TinyOS side, if this data element here is going to need to travel over a radio edge, it's going to need to be serialized and split up into different message size chunks. So that's all well and good and can be done with straightforward techniques. It helps the TinyOS programmer to not need to worry about that serialization or deserialization. But there's nothing particularly interesting or problematic about it. The more complex issue is dealing with the granularity of computation. So one of these data flow operators, when it fires, it essentially executes an arbitrary program inside. And it can run for an arbitrary length of time. In the TinyOS world, I mentioned we don't have threads. Instead, the execution model is that we have TinyOS tasks. And one task can run at a time exclusively on the system, runs until completion, and can post other tasks through a global queue. So what we need to do is we could try to execute an operator as a single task, but it would run for too long and starve out system tasks that provide important services like maintaining routing trees in the wireless network and what have you. So we need to have some way of splitting these tasks up into bite-sized pieces that are appropriate for TinyOS tasks. And the approach that we use for this could be called profile-driven cooperative multitasking. So what we do is we use our very fine-grained profile information to profile an iterate operator like this with a piece of code inside it, and understand the structure of its dynamic extent in terms of which parts of the code are contributing to its runtime. Now, in these sensing applications, typically we can assume that they're doing, when they do execute, they're running a fairly regular pattern of execution. So we extrapolate from the profiling results that if we want to divide one of these tasks up in the following places, we can map those dynamic locations back onto locations in the code where we can insert yield statements, including yielding at particular iterations of loops. So once we have that, the compiler can generate separate tasks that run up until a yield and then repost the remainder of the computation. And so that's how we address granularity for computation on TinyOS, to give you a sense of the problems involved. OK, so returning to this picture to finish the system architecture here, just having this data flow graph abstraction for programming some of these very small devices like TinyOS nodes is a big improvement. But we didn't stop there for two reasons. And one of them is that these graphs can get quite large. So you can imagine very large yet very regular graphs that you would instead want to write a program to construct. And that's exactly what we do here. The kind of source programs that I showed you earlier are actually programs that construct graphs. So that's what a high-level WaveScope program would be. And the WaveScope compiler up here, the compiler front end, which is shared between all these different backends, it accepts sample profiling data, which it uses to drive all of its decisions about optimization and about partitioning data flow graphs. Now, the second reason that we've introduced this, what I would call a multi-stage programming model, where we write a program that's generating another program in the form of a data flow graph, is that we actually want to have an asymmetry here, where we have a different feature set in the compile time language and in the runtime language. And the reason for that is that we want to have an extremely simple runtime language, both because we want it to be easily portable when we add new platforms, and because on some of these small platforms, you might not want to pay the price for some of these interesting features that you might want to have in the high-level source language, like higher-order functions or extensible records. So I call this asymmetric multi-stage programming because the different stages are in different languages with different feature sets. And you see this all over the place, especially in domain-specific languages. For hardware design is a common place where this multi-stage architecture pops up. BlueSpec is an example of a hardware design language that employs it. But also, we write programs that generate other programs in all kinds of different situations. The C preprocessor is a simple example, and Java programs generate SQL queries all the time. Now, in terms of my contributions to the system architecture that I brought up here, I'm responsible for the entire software stack here, and other people in my group serve as clients of the WaveScope system, using it in some of the different applications that I showed you. But I myself have also done a lot of the application development. OK, so zooming in here on the compiler, it's composed of a number of stages that we're going to talk about today, in particular these 4. And the first step here, WSeval, is going to take a source program and evaluate it to get out the dataflow graph. The rest of the compiler deals in terms of dataflow graphs and optimizing them. So first, the WSeval step. So the goal of WSeval is to take one of these abstract source programs that constructs a dataflow graph. So for example, here's a function f that takes a stream as input and produces a stream as output. And here's 2 invocations of the function f. We essentially want to evaluate this program and come up with something like this. So this is a textual representation of a dataflow graph here. It's a fixed dataflow graph in the sense that every place where you see the word iterate, it corresponds directly to a node in a fixed dataflow graph. So the goal is to go from here to here. What's interesting about our approach, our multi-stage programming design, is we're essentially generating the runtime program from the compile time program. You might call this partial evaluation, metaprogramming, multi-stage programming. Because of the structure of our particular application domain, we've managed to come up with a multi-stage design here that's rather unobtrusive and avoids any quotation and unquotation in constructing these code objects that are going to run at runtime. And the way that we end up doing the actual evaluation in the WSeval step is we run a simple interpreter that has a value representation extended to include stream values. A stream value is going to correspond to either an iterate or a merge. And the main of the program, if you will, returns a stream value. So that's a complete application. And once we've run our interpreter and we have a stream value in memory, then the final step is to unpack it back into code to get something like this. And that's our multi-stage programming approach.
So can you just briefly describe
Sure.
again, the things that are in the source language but not in the target language that you have to compile away?
Sure. So some of the features that we have up here are, well, in particular, in the language up here, we can wire dataflow graphs. The dataflow graph is kind of still in flux, but the dataflow graph has been fixed by the time we get to here. And if you look at the particular code that goes inside one of these iterates, the simple mental model here for programmers, by the way, is that everything outside of an iterate is going to go away at compile time, and everything inside an iterate is going to be a dataflow kernel that executes at runtime. So the question is, what are the language features that you can use inside that dataflow kernel? So we can use a type system to kind of separate these different layers here and make sure that you only use allowed features inside the iterates. The basic language model is the same in terms of the data model, and you can reuse a function either inside an iterate or outside an iterate. So that's fine, but in terms of some of the particular features, I mentioned higher order functions and extensible records, for example. We have those in the meta language, but they have to go away in the compile time language, but they have to go away in the runtime language. So those are two examples, and I could talk about it in more depth offline or at the end. OK, so the second step, in the second stage of the talk here, as I mentioned, I'm putting on my compiler and optimization hat. And we're going to be talking a little bit about the Marmot deployment some more. That's me looking for Marmots.
So it's a new language that you wrote, right?
Yes, it is. So a lot of what I'm showing you are a set of tools that work with dataflow graphs and are somewhat agnostic to what's inside them. But we've also gone and made a domain-specific language for writing these streaming applications because we feel that we can do more that way.
Question, how can we identify where the message comes from? Does it have some ID of the devices which initiated this message? So how can we determine this comes from, let's say, somewhere in the field, right, in this place?
Sure. So for example, if you had some point in the graph where you had high in degree and you wanted to know what the origin of the different messages are, well, you would have to tag them yourself because the basic computational model doesn't have that built in. Of course, it would be very easy for you to do so. So for example, when that merge that I showed you, it doesn't change anything in terms of the data that it passes through. but you can tag the tuples that are flowing through ahead of time so that you know which one they originated from. One place this is very relevant is when you're dealing with a sensor network like this, you very often want to put the node ID into the record that you're sending along.
So essentially when I go through a data flow graph, every node can put its ID, right? So I know the whole route, right?
Sure, you can do that. Yeah, absolutely. So by the way, compared to a lot of other stream programming languages like Streamit, the dataflow model is pretty rich here. So this is a high-level, type-safe, garbage-collected language. You can have lists, you can have arrays, you can have records that are passed in these data objects. Or that are passed in these tokens that go through the dataflow graph. So by all means, build whatever data structure you like within the data that you're passing along that can record whatever you want.
So essentially, there are no properties for optimization. I mean, I could optimize if I knew what each of the event has some properties. I would be able to optimize. But now, if they just, don't have any opportunity to optimize.
So that's an excellent point. Is that there's a tension here where if you bake more into the model itself, you might expose more information to the compiler that it could use for optimizations. But of course, then you've complicated the design by baking in particular features into the dataflow model that might not be exactly what some future user wants. So we've gone for a very simple core model. And actually, I'm going to address exactly that point when we talk about domain-specific optimization. So there are particular domain-specific optimizations we want to capture, but we don't want to commit our compiler to them in the sense of baking them in directly to our implementation for a variety of different engineering reasons. So I will get to that actually right now. So the step right after WSeval is that we apply use an optimization system based on algebraic rewrite rules. So these pop up in various places in some general purpose compilers and also in some database systems. So rewrite rules are simply statements that the end user, or more likely the library writer, can put in their code that say when I see a pattern on the left, when I match a pattern on the left, I want to replace it with an expression on the right. So for example, FFT of inverse FFT of x should just be rewritten to x. If we're dealing with windowed streams of data structures essentially, changing the window granularity twice is redundant, so you only take the second one. Those are two rewrite rules that are in our libraries. So you might immediately notice a problem here, which is, based on what I've told you so far, WSeval is going to spit out a dataflow graph consisting only of these iterated merge nodes. So essentially an anonymous dataflow graph. There's no notion of rewindow in that dataflow graph. There's just a bunch of black boxes with compute inside them. So we have a bit of a tension here in terms of where we do these algebraic rewrite rules. And the way that we've solved this problem is that WSeval is run twice. So in particular, the first time through, we want to leave any names that are mentioned in these algebraic rewrite rules, we leave them abstract. And that enables us to reduce the program as far as possible, possibly bring these two rewindows together from distant points in different libraries that they originated, but without reducing the program so far, essentially without inlining the definition of rewindow to actually generate a series of iterates. So then once we've done that first WSeval, we execute our rewrite rules until fixation, until there are no more. We greedily run all the rewrite rules we can, and then we go back and do WSeval a second time, which actually gets us down to a plain anonymous dataflow graph of black boxes. And all of the subsequent steps of the compiler deal only with that dataflow graph representation.
One of the techniques I remember from the FFTW work was having rewrite rules that were not necessarily improvements and then wanting to do a search at the end. Is that something that is, what are your thoughts on that?
Sure. So these are absolutely not the most sophisticated kinds of optimizations that we could apply. This has worked well for us. And it's been a way to capture some domain properties in an extensible way that we can apply to different domains. But it's certainly, you might say these are we can only capture a small class of interesting domain properties in this way. Certainly a system like that, where you had a more interesting control policy for applying rewrite rules, would be one way of generalizing this. But for us, the main thing was to see how far we could get with this to try to encode domain optimizations for complex event processing, for digital signal processing, without having to bake them into our core compiler. And this was one relatively straightforward way of doing so. And in particular, we didn't do this just to catch opportunities for optimization in existing programs. It's not just to speed up programs. We also find that algebraic rewrite rules are very useful for enabling better library design. And one example of this is if you're trying to design a digital signal processing library, then it's a cognitive burden on the user to have a mix of different functions in frequency domain as well as in time domain. So wouldn't it be nice if we could write our library so that everything is simply in time domain? But of course, that would be crazy, because then the user would compose two black box library functions, A and B, and they would turn out to both internally prefer to operate, let's say, in frequency domain, but just convert back to time domain for the purpose of communicating between them. But if we can count on our system to do some of these basic algebraic optimizations, like eliminating this IFT and FFT, then we can write our libraries in this way and enable simpler interfaces than we would otherwise be able to. And this is, for example, what we've done with our DSP library.
So you're doing this by breaking up the data flow boundaries, the actor boundaries?
Well, there are no actor boundaries. So that was part of the point, is that you...
Just a numerical library. This has nothing to do with the actor structure, or the data flow structures.
Well, I'm not sure I caught that question.
Is that black box a actor or not?
So this black box was not an actor.
Okay.
Yeah, so I'm sorry. And that's actually a good point about the slide, is it looks like these are actors decomposing into smaller actors. But yeah, this was just a visualization to be helpful. So what you'd actually have is you have expressions in the original source language, things like rewindow of stream expression. And that is a function that is going, when it's inlined, will introduce a bunch of iterates, which themselves correspond to actors. Once we get down to just the actor model, the data flow model, then we just have a bunch of anonymous data flow operators. And we can't do any algebraic rewrite rules at that point. So we have to catch them before we get to that point. OK, so once we do get ourselves down to just a data flow graph, then the next important step is to profile it, as I mentioned. So every data source in the program is associated with some data sample. Now, it's typical in this embedded sensing domain that a first step will always be to go out into the field and capture some raw data so that you can even formulate your experiments and test your algorithms. For example, in our Marmot application, we have a terabyte of Marmot audio data on a server that we use for testing. And there are more ergonomic ways to do this probably, but currently we simply have a kind of a macro switch that you use in the source code to specify for every input source where you'll get a sample data file if you're not using the raw sensor source itself. So when we do the profiling step, the goal is to pump this sample data through the data flow graph and make observations about the data rates that we see on the edges and the execution times for the nodes themselves. So that's important information about the data flow graph based on the profiling data. But there's a separate step that the user also has to do just in time as they're about to do their deployment on a wireless network. And that's to profile the network channel capacity in the deployment environment. So for one of these mesh networks, the actual bandwidth that we can get out depends on a number of conditions. So you run a portable WaveScope program that characterizes the channel capacity and gives you basically a per node maximum send rate that we're going to use to formulate the optimization problems that I'm going to talk about. All right, so this profiling data is going to drive all the subsequent optimization in the system. A very simple example of this would be the batching optimization that G mentioned earlier, which is if we notice that an operator is lightweight in the sense that it runs quickly and that it's receiving a high frequency of small data items as input, then regardless of what platform we're running on, it's going to help to batch together those elements for bulk processing. And we get some speed up for that, whether we're in a single-threaded or multi-threaded context. So now I'm going to switch back to the Marmot application, talk a little bit, and evaluate the system.
Could you talk a little bit about why profiling the network is a robust step? Why?
Sure. So I will happily confess that our system presently does a lot of offline optimization. So you might very well worry about dynamically changing conditions, and currently we don't have a good way to re-optimize a given deployment. Now, it happens to be the case that when we do these deployment in remote areas, we don't have to worry about 802.11 interference or what have you. So it's a little bit more, it's reasonable in our case to just profile the network once, make some assumptions about the stability of those measurements, and then base our optimization decisions on that. But certainly future work would include looking at more adaptive mechanisms. A simple one being simply rerunning the whole thing every 30 seconds, 60 seconds, what have you. OK, so back to Marmots. The Marmot localization application consists of 3 steps. The first one is that we're going to listen continuously to one of those 4 audio channels on a given node for a sound that might be a Marmot call. And basically, this just means a spike of energy in a certain frequency of the band that penetrates our adaptive threshold. So then we've got a Marmot detection event that happens during a certain time range. We want to synchronize the audio from all 4 microphone channels on that local to that node and package up together the snippets that, from that time window where there was a detection. Given that information, those 4 snippets, we can do a direction of arrival search through possible angles of arrival for the sound that's going to give us a radial probability map for where the sound might have come from. Now, there are some asymmetries that we can't overcome here. So one of these radial probability maps for an individual node is going to be sort of multi-lobed in that there are ambiguities. But the basic idea of the application is that when we fuse the information from different nodes, we have enough information to figure out where the sound came from. So the end result, the third step, is to fuse the information from all the nodes and come up with a likelihood map where this is a heat map where the color represents the probability that sound originated at that point, and we guess the animal to have been at the point of highest likelihood. And this pops up on my screen on my laptop in real time in the field. So with modest simplification, this is the data flow graph that corresponds to that application. We've got our raw audio data coming in. We've got our first step where we detect Marmot-like sounds. We sync together the 4 channels of audio. And by the way, internally, this is going to be based on those merge operators. And then we do that direction of arrival computation I mentioned. And this is a relatively expensive second step, especially when we're executing on the sensor node itself. It takes about 2.5 seconds. And then we send the output, which is simply a small array of probabilities for that radial probability map, across the network interface and associate events temporally and compute our pseudo-likelihood map here. So one of the first things we noticed when we were out in the field for 10 days was that the Marmot calls were burstier than we thought. And one Marmot would chain react off the others. And we would overwhelm the CPU on the embedded device and lose data. So it helped that we could just change a line of code, because this was all in a unified system, to move that second step to the server side of the computation, where now we send those 4 pieces of synchronized audio over the network interface and do all the direction of arrival computations on the more powerful base station backend. OK, so still in the single-threaded case, talking about the embedded node, we saw a nice speed up in the execution of our implementation relative to a previous implementation that a different group of graduate students had done of a subset of this system a year earlier. So it was fortunate to have that apples-to-apples comparison. And there are 2 contributors to the performance here that I'm splitting out as the event detection itself, the operators that I showed you, and the basic data acquisition overhead. So we saw a speed up in both of these components for 2 different reasons. The yellow bar here essentially got smaller due to the optimizations that I mentioned, including batching and the algebraic rewrite optimizations. And the reason that the purple bar got smaller is a little bit more subtle. So the C code that the original implementers here wrote was using a framework called the MSTAR framework for doing embedded sensing applications. And the MSTAR framework provides a lot of flexibility to the user, except it does so in the form of runtime services that exist in separate processes and connect together. And on this ARM platform here, there was a lot of overhead to those kinds of runtime services. So our system, by contrast, is a very offline, whole program optimization-oriented system that can smash everything down together and run it in a single system process. And that greatly reduced the overhead of our data acquisition itself.
So you said this is an ARM system, but is it the sensor system?
So this is the VoxNet
Okay.
platform with the 4 microphones. Yeah.
Okay.
Yeah. So it's not as low power as some of the devices that I'll show you. But in this case, it was great. We wrote less code. We got more performance. And it also had a bit of a practical benefit, because the extra CPU cycles that we freed up enabled us to implement new tasks in the field. Like we implemented a spill-to-disk task that archived all the data to flash memory as well. And that was useful. OK, so switching from the single-threaded case to the parallel case. As I mentioned earlier, synchronous data flow models exhibit very nice parallel performance on a number of different parallel architectures. So here we're going to look at the intranode parallelism on, say, a multicore. And with our asynchronous data flow model, we can apply some of the same optimizations that we see in the synchronous data flow world if profiling data gives us enough information to do so. So 2 common optimizations for these data flow graphs are to fuse nodes together, fusion, and to recognize stateless operators that we can split apart for data parallelism. So that is to say, if I have a stateless operator, I can make 3 copies of it, and then I can round-robin data elements, stripe them across the different workers, if you will. So a great policy for these two optimizations in the context of synchronous data flow can be seen in ASPLOS 06. And we've managed to successfully apply these optimizations as well in asynchronous data flow using our profiling data. So here's an example of that expensive second step to the Marmot application, the direction of arrival search, running on an SMP. In this case, this was a 4 quad-core Barcelona machine, but you could also imagine running on my laptop in the field. So this is relevant either when we're processing lots of data offline for testing or when we're in the field and using a multi-core base station. So one thing we see here is that fission by itself doesn't perform as well as first doing fusion and then fission. And this is a well-known property because you don't want to generate a data flow graph like that. If you run fusion first, you'll instead generate this data flow graph and omit spurious splits and joins. So ultimately, what we see here is that when we're processing Marmot detections, what we're doing here is we're parallelizing the work between consecutive Marmot detections. So we're round-robining the work in consecutive Marmot detections to different workers on different cores. And we achieve a reasonable speed up there, but it doesn't reduce latency of processing an individual detection at all. So I'm going to tell you a little bit about one more optimization that our compiler does, which to our knowledge is unique to WaveScope among stream processing systems. And this is an array-based kind of fission, where if the compiler can determine that your operator is producing an array as output, and an example of that is that direction of arrival computation that produces an array of probabilities, then we can split it up into a number of workers that take the same input and produce a subsegment of the array, which can then be stitched back together to produce the original output. And if we apply this, if we enable this optimization in our compiler, we see a speed up that looks like this. So the important thing to note here is that we get a nice speed up until about 6x, at which point it falls off because we're splitting the array into smaller and smaller pieces and not deriving any benefit from it. But at this point here, we achieve 6x improvement in both throughput and latency, which is relevant if we're processing in real time on the field. And also, it's worth noting that my laptop doesn't have more than 6 processors already, so this is the appropriate form of optimization. Now, in the present implementation, this array fission optimization precludes the application of normal fission. Now, if our compiler did a little bit more work and would reprofile different configurations of the graph rather than just running profiling once, it might be able to find out where that local optima was and apply this optimization in moderation. The ideal thing to do here would be to apply normal fission and then subsequently apply array-based fission in concert so that we would end up producing individual data elements as subsegments, stitching them together, and then interleaving them. And that would give us the best of both worlds here and would be the right thing to do. OK, so now I've talked about the single-threaded context. I've talked about parallelism inside a given device. And finally, I want to go ahead and talk about the distributed context between different devices. So I'm going to show you our initial solution for program partitioning, for automatically dividing data flow graphs between different platforms. OK, so back to one of these data flow graphs. Typically, the inputs to a data flow graph are sensors on an embedded device, and the outputs go either to a database or to the user on some back-end base station. And the goal of the partitioning step here is to assign all the operators to one platform or the other, which induces a cut that has to go where the edges have to go across the network boundary. And given one of these partitioned data flow graphs, we expect the compiler and toolchain to be able to produce a binary for each platform and disseminate the appropriate subgraph to it. Now, in a sensor network type deployment, we have n nodes rather than just one, so we can replicate that portion of the subgraph across all those nodes. And for the rest of this talk, let's just assume we use the same partitioning, but we could use different partitionings at different nodes by running the partitioner multiple times. Now, the fact that we've replicated a subgraph of our data flow graph here has interesting implications when some of these operators are stateful. And you can ask me about that offline, or I can refer you to the paper for that tricky bit. OK, so the way we formulate the partitioning problem here is that given our profiling data, we essentially have weights on our edges and on our nodes, on our edges and on our vertices that correspond to CPU cost, to compute cost, and to bandwidth on the edges. So there are two relevant numbers here for a particular cut. One of them is the sum of the CPU cost on the embedded node, and the other one is the sum of network cost on the edges that are cut. Now, we could also look at the sum of the load on the server side, but for our applications, the server is effectively infinite capacity relative to the embedded node, so we don't worry about it for this optimization problem. All right, so this is the graph, minimum cut graph partitioning in general is NP-hard, and we have formulated the solution to this problem as an integer linear program, also an NP-hard problem. And our formulation goes something like this. Well, an integer linear program is a collection of equalities and inequalities over certain variables. Here we introduce a set of variables corresponding to each vertex in the graph that are going to take on the value of 0 or 1, depending on whether or not that operator is assigned to the sensor platform or the backend. We also introduce a set of variables for the edges that are going to correspond to 0 or 1 based on whether or not it's a cut edge. And then our goal is to enforce resource bounds, where we say that the sum of CPU usage across all of the operators that are assigned to the embedded node must not exceed some cap on CPU usage. Similarly, we restrict network usage such that the sum of network usage across cut edges must not exceed some cap in, weighted by all of that profiling data that we gathered. And finally, our objective function that we're minimizing here is going to be a linear combination of CPU usage and network usage. We're enforcing resource bounds and minimizing some combination of those two resource usages. Now, this is all very straightforward. The only tricky bit here is how you relate these f and g variables while keeping the problem linear rather than quadratic. And for that, I can refer you to the paper. So it looks like there are 3 parameters here. There's c, n, and alpha. Now, c is typically 1 because these compute measurements are measured as a fraction of the capacity of the device that you're profiling on. And we profile on all of the embedded devices that we're interested in using. The network capacity in here is set by that network channel characterization tool that I mentioned. And finally, alpha here could be set by the user as a way of trading off their optimization priorities for compute usage versus radio. But typically, this linear combination here serves as a proxy for energy usage, in which case you can set alpha empirically based on measurements of the energy cost of the CPU versus the radio.
That's the energy usage for the entire network?
No, this is for each individual node. Yeah, so by the way, I'm assuming a relatively simple, for this partitioning problem, I'm assuming a simple communication organization where all nodes are communicating to the server. And I'm not taking into account, yes, I'm not modeling the uneven energy usage that results from the multi-hop network. So that's just not something that we're modeling. But it's an important point. OK, so to evaluate this, go ahead.
I didn't understand. When you said I'm looking at the minimum over all nodes, are you saying then that this is like minimum max? Is this a minimum maximum energy usage?
Oh, no. So this is basically this partitioning algorithm is figuring out what's going to happen between a given embedded node and a server.
I understand that. Okay,
yeah.
Got it.
And we're just trying to minimize that partition of the data flow graph. And then a simple thing to do is to take that partition and use it on every node.
Sure.
But you could do more complex things as well. OK, so for the evaluation here, we take a collection of different embedded devices that we're interested in programming, including the little microserver that I showed you before, and our low-power embedded nodes that we've extended here with a custom audio board for doing the speaker detection application that I'll tell you about in a second. And we've got our smartphones. And we see a different mix of sort of CPU power and radio power here, changing the optimization criteria. And finally, here's an example of a Meraki outdoor base station, which has a very weak CPU and a strong radio. So given those platforms, we take a couple of our applications here. Our human speech detection and identification application, which has a very simple processing structure, a linear pipeline of operators that's going to pop up in the evaluation in the next couple slides. And we also took another one of our applications, the opposite end of the spectrum in terms of complexity. Our EEG application is 1,400 operators in a relatively large data flow graph, applying a cascade of filters to each one of the 22 channels. OK, yeah.
So is that after your profiler spit it out, or is that the closer to what the source code is?
So this is after the profile. This is the actual data flow graph. Yeah.
Okay.
Yeah. Yeah. So by the way, the source code is relatively simple. This is there's less source code in this application than there is in this application. And by the way, this is the kind of visualization the compiler spits out using GraphViz. This is the profiling data in terms of the colors of the different operators. So we can also look at the network versus CPU usage signature of a given application. This is the speaker detection application laid out with its linear pipeline of operators laid out across the x-axis here. And so we look at the cumulative CPU usage in red as we push more computation down into the embedded node. And at the same time, we look at the bandwidth of that single edge that needs to be cut as we're splitting this data flow graph. So it's a linear pipeline. It's very easy to think about the space of different partitionings here. Now, we can immediately see that Well, like most of these sensing applications, the general trend is towards data reduction. We're taking large data volumes at the input, we're extracting features, applying compression, and somehow or another restricting the volume of data. But of course, this is not a monotonic progression. We can see here that FFT, for example, in this particular application, keeps around both the frequency and time domain, so it increases the volume of data at the expense of spending some compute as well. So it wouldn't make a lot of sense to cut this application right after FFT, right? So we can see by eyeballing this that there are only a few reasonable cut points. Basically, send across the raw data over the network, or do enough compute that you can get to filter bank here and have actually reduced the data a significant amount. OK, so that's what we can see just by eyeballing it. Now, if we run our partitioning algorithm many, many times to generate a landscape of optimal partitions, we can get something that looks like this. So this is for a single channel of the EEG dataflow graph of the EEG application here. A single channel of this graph has about 80 operators in it. And what I'm doing here is I'm essentially changing that C parameter, if you remember the ILP formulation. So trust me for now that changing the compute on the embedded node is equivalent to changing the data rate at the inputs. Because for these applications, data rate scales linearly with compute costs. So what we're doing here is we're looking at different hypothetical data rates, asking how would this application partition if we change the input data rate to the application. So if we're running at a low data rate, we see that we can fit all of the operators down inside the embedded node. But as the data rate increases, I only show two platforms here. As the data rate increases, the amount of compute that we can afford to do in the embedded node drops off. And the reason we see it drop off somewhat continuously here rather than just fall right off a cliff is that there are multiple points within this cascade of filters where the data volume is reduced. So you can go partway down one of these processing paths and get a partial data reduction for a partial compute effort. Yeah?
Why does changing the input rate now also change the bandwidth demand?
Oh, it does. It does.
But you said you were just changing C here.
Yes. So I forgot to mention for this graph, in the objective function, I'm setting alpha to 0. So I'm minimizing. I'm just capping CPU and minimizing network usage. That's the goal for now for this slide. Oh, another question?
Do you have any need to go back and forth between the low power nodes and the high power nodes, or after you do the transition, you just continue on the high power node? For instance, if you're about to send out data, everything will happen on the cell phone or the server, right?
Right.
If you want to do the FFT locally, then after you switch to the higher end node, then there's no reason to come back, right?
Right.
So there's always one switch point that you want to find out, right?
That would simplify it, but it's not always the case. And I'm lucky to have a whiteboard right here. One simple reason why that wouldn't always be the case is if you have two data paths that are coming together, if you have a merge point, and one of them is very expensive, but the other one involves data that's local to the sensor node. So I might want to export this expensive operator off to the server, and then have its output come back to be merged with some locally produced results on the sensor. So in general, we might want to go back and forth. But certainly, there are a lot of applications that do meet the constraint that you mentioned.
So you can know this information offline. Is that correct?
Well, yes, with profiling data, you can know this information offline. But
My next question is, do you really need any linear programming propagation for that, or is it a simple search on the graph to find single points of switch and optimization there?
No, I'm pretty confident that it is in fact an NP-hard problem, what we want to do. So one thing you could think about is with one of these very large graphs, you essentially have, you could think of this as bin packing, or you could think of it as graph partitioning. We're only interested in what we're packing onto the embedded node. But we could have a very large graph with a number of independent decisions that have to be made that all affect the compute usage on the embedded node. So it makes it a rather difficult optimization problem. And as a human being, it's difficult to look at these very large data flow graphs and even get a qualitative sense of how you want to partition them. So to give you one example of that, with this big EEG data flow graph, when we first were looking at it and trying to manually partition it, it wasn't at all clear to me whether or not an optimal partition of the graph would be horizontal, doing processing on all of the channels half of the way, or vertical, doing processing on some of the channels all of the way. And it turns out to be vertical. As you increase the CPU cap, you fill up one channel at a time. And we discovered that by running our partitioning algorithm. So this shows similar results for our speaker detection application, except with the axes flipped here. So on the x-axis here, we have that handful of reasonable cut points that I showed you. And the y-axis shows the predicted throughput of the entire application running at that cut point. So and by the way, this is just taking into account CPU constraints and not hard network bounds. So for each of these different platforms, we can see that the two weakest platforms, those low-power embedded nodes and our Java-based smartphones, cannot keep up with the native data rate of the application here, which is the horizontal line, after the first cut point. So then we're stuck between a rock and a hard place, because we don't have enough compute to do everything we need to do on the embedded node, and we don't have enough network bandwidth to get all the data we want out of the system. So something's going to have to give. And that, I think, is where things become really interesting in making these hard trade-offs. And our system can help with that if we close the loop in the following way. So given CPU and network bounds, our algorithm can give you an optimal partitioning of the dataflow graph if it exists. And based on one of those partitions, we can estimate the total throughput of the application. So we close the loop here by doing a binary search over hypothetical data rates to find the data rate at which the maximum possible throughput will be achievable. And in this speaker detection application, that happened to be right after filter bank was the optimal point. But this is still a prediction based on all the profiling data that the system has gathered. So the final bit here to close the loop is to go back and look at ground truth data. Now, I noticed that I'm actually running out of time, so I might go ahead and refer you to the paper for this evaluation. The bottom line is that if you take a test bed of nodes and we measure it at every possible cut point, and it turns out...
Right.
Oh, sure.
We actually have the room until noon, so you can run a little bit over. People may get a little
Okay.
fancy after that. But
Okay.
if there's something you want to say, you can say it.
Sure. All right. Well, here we go. I will go through the slide in detail. So for the speaker detection application, we've got that linear pipeline. We can evaluate it on a test bed of 20 of these low-power motes arranged in a multi-hop network. And we can see what the total application throughput, that is, how many speaker detection events do we get back to the user for each one of these cut points. And this graph here shows a 20-mote network compared against a single mote network. And it's not normalized based on the number of nodes. We're just looking at the absolute number of detections per second that we get through the network back to the user. So what we can see here is until the very last Kepstrel phase, which is a very compute-intensive phase, this is actually a totally network-bound problem, so that the one mote can do as well or better than the 20-mote network. And when we get to that very last cut point, the 20-mote network is going to have 20 times more small CPUs than the single-mote network, so it'll do quite a bit better in terms of application throughput. So now if we tease apart the different contributors to data loss in the system, you can basically lose data either at a sensor because the CPU was too busy to pick it up, or you can lose data at the network interface because the network was too congested to convey it successfully. So if we look at these two different sources of loss, we can see the percentage of input events that we pick up at the sensor sources declines as we push more compute onto the node. We're not able to keep up with the compute load. So we're running in a kind of overload situation here. Whereas the number of messages that we get through the network, the percentage of messages we get through the network, is very nonlinear here and increases drastically when we've reduced the data far enough that the network can tolerate it. So what we're interested in is the product of these two loss factors, which is this blue line here. And we can see that the best empirical cut point here is right after filter bank, which is what the model predicted. So by the way, you can see that in this case, on a very low power platform, we're only, even at the best point here, we're only delivering about 10% of the ideal application throughput. But in some applications, that's perfectly fine. In this case, we have a speaker detection application that in its original formulation would poll 40 times a second to listen for a speaker. In this case, on one of these low power nodes, we can only poll 4 times a second, which is still a useful application behavior. And one of the lessons here is that even on this weakest platform, it's important to pick the right cut point, because several of these partitions resulted in no data at all. And the ones that did get some data back, the best one was 20 times better than the worst of them. So it's important to pick the right one, even with as simple as a data flow graph as the speaker detection application. OK, so for the rest of the evaluation, I'll refer you to the paper. And I'll just wrap up here by zooming back out.
So just a clarification. So in that ground truth experiment, what was the data generating source?
So in this case, it was a microphone. So we built that custom audio board that we attached to the Telos motes. All right, so zooming back out here a little bit, I mentioned heterogeneity, both in hardware and software, as one of the barriers to being able to program these kinds of distributed applications. And I want to make a few comments about where that heterogeneity is leading us. So first of all, in the last 10 years, we've all gone from having a relatively simple computing environment around us to having a veritable personal heterogeneous cluster of devices. Our single core has become a multi-core. We now have programmable GPUs in our personal computers. A lot of us might have gaming stations that might have interesting parallel processors in them and additional programmable GPUs. But perhaps most starkly, our cell phones have become smartphones. And those smartphones already will have a collection of different ARM cores in them, a DSP, possibly an image signal processor, and another GPU. And these things are all over the place. And in the future, this heterogeneity in architectures is only going to get more severe, especially as some of these low-power devices enter our infrastructure and our appliances. And my vision, what I would like to see happen is rather than all these components remaining sort of fixed function and programmed independently, I would like it to be possible for an application to flexibly touch many of these separate components at once, which means dealing with many separate architectures. And also, there's heterogeneity on the networking side. Such a hypothetical application also has to deal with communicating both over incredibly tight links between different cores on the same chip, all the way down to incredibly weak links between these low-power radios, spanning what we normally refer to as parallel and distributed computation. Now, I'm optimistic about this because I think that we can make computation much more flexible and we can build applications across these heterogeneous architectures. And I think that the way forward will involve a combination of two things. We want to have high-level domain-specific representations of computations. And we also want to get a lot better at modeling, measuring, and auto-tuning the implementation of these computations. And you can already see successes of this dual approach in certain projects. I'll mention, for example, the Spiral project at CMU for DSP-type computations. That's a domain where they have high-level structured representations. They know enough about the search space that they can effectively auto-tune to map these computations onto a wide range of different architectures. Ultimately, I think that the vision that I'm most inspired by is that for whatever reasons, in the future, the relationship between a computation and its physical instantiation is going to become more indirect, more fluid, more liquid. Now, a lot of people, I believe, are inspired by this same vision, though they use many different words to describe it. Some people talk about programming clouds. Others talk about programming grids. Some people talk about smart dust, motes, or amorphous computing. But I think a lot of the motivations are similar here. And a couple observations I want to make. The small and the large have a lot in common here in terms of if we look at our high-performance big iron computing environments versus our low-power embedded environments. Increasingly, we see things like if you look at the small processing elements in a parallel architecture like Cell, the individual SPEs, they don't belong to the normal memory hierarchy, and they have their own small memories, so they start to look a little more like an embedded device. And similarly, it's become some groups I've heard are looking into using more low-power processors to build high-performance computing solutions. So we can find ourselves back in the same place here with dealing with smaller, resource-constrained platforms. Now, a major axis of variation in these different systems here is heterogeneity versus homogeneous networks. But it's one point that I want to make in favor of looking at heterogeneity seriously is that it's hard to get rid of it. Even if you start off with a big computing infrastructure where all the nodes have the same capabilities, if you're, for example, dealing with heterogeneous workloads from many different users, you can all of a sudden find yourself in a situation where your computing landscape looks very heterogeneous once again. So heterogeneity will always come back to bite you. And in conclusion, the WaveScope system here has taken a small step towards making computation a little bit more liquid. And the system itself is available and is used at a handful of places. And even if you don't like the automatic partitioning, the tools for dealing with dataflow graphs, visualizing them, profiling them are very useful. And in terms of the intellectual contributions here, I've shown you a new algorithm for partitioning dataflow graphs. We've looked at a little bit of the novel multi-stage programming architecture of this system. And I've talked a little bit about some of the innovations in the back end to be able to target very small devices. Thank you. And I'd be happy to take any questions.
By backend, you mean the compiler backend?
Oh, yes, that's right. That's right. Good point.
Other questions? Let's thank Ryan.